So hello and welcome back. So in this video we are doing this example which is related to exponential functions and the properties of exponential functions. And the question is the relationship between the elapsed time t in decades since Barney started studying the population of and the number of tigers n of t is modeled by the following function. N of t is equal to 710 times 8 by 125 raised to the power t. So now the tiger population loses 3/5 of its size every how many decades. So there are a couple of things that here you need to understand. First, this is a relationship between n of t, which is the number of tigers, and t, which is the number of decades passed. So here this relationship tells me that in the beginning there were 710 tigers, and then with every incrementation of t, basically a factor of 8 by 125 is being multiplied by the whole population of the tigers. Because let's say you have this table t and n of t. If you have this, so what happens here is that when t is equal to 0, the initial value of the function is 710. So you basically have 710 because t is equal to 0. So this whole thing becomes 1. 8 by 125 raised to the 0th power is 1. So you have 710 tigers. When you have 1, when t is equal to 1 after 1 decade, then the population is 710 times 8 by 125 raised to the first power. When t is equal to 2, the population is 710 times 8 by 125 raised to the second power. So it's again times 8 by 125. So basically every time you're incrementing t, you are multiplying 8 by 125 by the previous population to get the new population, and this keeps going on. Now and one more thing that you need to understand is that multiplying 8 by 125 by any number, if you write x into 8 by 125, you are actually calculating a percentage of x. And what is 8 by 125 is nothing but 0.064, I suppose. 0.064. So that is x times 0.064. So 0.064 is nothing but 6.4%. So you can rewrite this as x times 0.4%. So this way, when you are multiplying x by 8 by 125, you are actually calculating 6.4% of x. That means whatever x was, 6.4% of the x is remaining, and 93.6% is lost. So basically here what this means is that 6.4% of x remaining or left and based on 6.4% that is left, then you have 93.6% lost. So this is one thing. And then now the problem is that here the common ratio of this function is 8 by 125, but the common ratio of the question is in terms of some other common ratio. So it says the tiger population loses. So here the tiger population is actually losing something, because every time 8 by 125 is multiplied by the output of the function, 93.6% of the population of the tigers are being lost. 93.6% is being lost in every decade. Now the question is asking the tiger population loses 3/5 of its size every how many decades? So I know that the tiger population is losing 93.6% in every decade, but 3 by 5 is actually 60%. So 60%, losing 60% means that 40% is remaining. 40% remaining, that means let me do it this way. So if you had this basically this equation in the form n of t is equal to 710 times so losing 3/5 means remaining 2/5, so times 2/5 raised to the power t, then you could say that every decade 2/5 of the population is remaining and 3/5 of the population is being lost. And that's basically the same thing that is being asked here. The tiger population loses 3/5 of its size every how many decades? So now, but the problem is that the common ratio here, which is 2/5, which I need to answer this question, is not the same common ratio that I have here. So I have to do something to this equation so that I get somehow this common ratio so that I can answer this question. So I can rewrite this equation as n of t is equal to 710 times 8 by 125 raised to the power t. So now I need to somehow make some changes to this common ratio to make it 2/5 instead of 8 1/25. I need to make it 2/5. So what I'm going to do is I write this as n of t is equal to 710 times, I write this as 2 cube, and I write this as 5 cube. And the whole thing is raised to the power t. And then what I'm going to do is basically 2 cube by 5 cube is nothing but 2 by 5 whole cube. So I write this as n of t is equal to 710 times 2 by 5 whole cube whole raised to the power t. Whole raised to the power t. And so a raised to the power b whole raised to the power c is equal to a raised to the power b into c. So then I can rewrite this as n of t is equal to 710 into 2/5. So 2/5 here is my a, and then I can rewrite this whole thing as 2/5 whole raised to the power 3t based on this. And now that's basically what I needed. I needed this ratio, and this ratio tells me that 2/5 of the population of the tigers is remaining and 3/5 is being lost, because 2/5 plus 3/5 is equal to 5/5, which is equal to 100%. Now, where was I? I don't know. So now basically every time, every 1/3, basically when I need to form a table here again. So I have a table here, and here I have t and n of t. And so when t is equal to 0, again your output is 710. When your t is equal to 1, then you have 710 times 2/5 raised to the 3rd power. So it's 2/5 times 2/5 times 2/5. So it's actually times 1/25, right? As it was before. So this is not what I'm looking for. I want to somehow do something, basically deduce something here, so that this index becomes 1. I want to know when this index is 1, so that only one factor of 2/5 is being multiplied here. So, and that happens when t is equal to, so 3t is equal to 1. When is it 1? T is equal to 1/3. So if t is equal to 1/3, then 1/3 goes here, this whole index becomes 1, and then my output is 710 times 2/5, because this becomes 1 and this becomes 2/5 raised to the 1st power. So basically t has to be 1/3 so that this index becomes 1, so that one factor of 2/5 is multiplied by this 710, and that means 2/5 of the population is remaining and 3/5 is lost. And 3/5 is lost, loses 3/5 of its size, exactly the same thing that I was looking for. And in this case, my t was 1/3 of a decade. So 1/3 of a decade is nothing but basically 0.33. So let's say 0.33 of a decades. In 0.33 of a decade, I'm sorry. I don't know where my problem was. Oh no, sorry. Or you could say in 1/3 of a decade, the tiger population loses basically 3/5 of its size, or basically in something around around 3 years, the population loses 3/5 of its size. So that's basically how you solve this problem. Thank you.